Yeah, please.
I'm very interested about the size difference. Obviously, this correlation with the nucleosome fragments is too interesting to be ignored.
Sure.
I wonder whether it reflects some kind of differences in epigenetic modification. If yes, can you explore this difference? For example, epigenetics between the baby or the tumor with the normal cells, normal DNA in the blood, and can you explore that to design even more accurate testing?
Exactly. We're actually working on that. We have actually recently shown that you can actually decipher the fetal epigenome by using this way. And that is very exciting because the epigenome, as you know, can change. Actually, for those of you in the audience, so epigenome means the biochemical modification of the genome. So the genome will be ACTG, but then we're talking about decoration, the change of that ACTG. And of course, some recent data suggests if a mother is diabetic or different, if a mother smokes, etc., or if a baby is conceived by using test tube baby technology, in vitro fertilization, they can all change the epigenome. So I think that by use of this sort of technology, we can actually monitor how the epigenome changes. So we are working on that.
Professor Yang?
Yeah, thank you, Dennis, for a great talk, and it's great to see that you not only contribute to the advancement of science, but also see your research results that actually contribute to the improvement of health and saving lives. That's a great accomplishment. I have a couple of questions. First of all, regarding the size-based diagnostic, do you find out there's some kind of correlation with aging, with a different age, with regard to the size in terms of distribution?
The age in general of people.
Yeah.
Right. We haven't have that systematically, but I think that would be one of the things that we'll be looking at. But on the age side, actually, at the moment, we're thinking about the methylation, the epigenome. As we get older, we might be able to do something in the blood to monitor that change.
Yeah, the other question is about, I think you also pointed out very importantly the ethical issues of these DNA. Right now we're moving into the genomic era. And actually last week I think that you also learned there's a big controversial, there's a paper published by a research group in China using the CRISPR technology to edit the human embryo. Yeah, so that's actually quite a big controversy. Now, but I mean for the society overall, it's very difficult to stop somebody from using the advanced technology for whatever personal or the gains, okay, financial or whatever else purpose. So how do we, as a scientific community or as a society, can set up some kind of a line, a red line there to prevent people from crossing that? Thank you.
Well, I think actually that Hong Kong probably should be more proactive because currently in many medical advances, Hong Kong has always been trying to follow what the international guidelines has established. But I don't see any reason why we should just be follower. Why don't we create our own regulations and guidelines and let other people look at that and may consider following us. So I think we should be more proactive, especially this technology is, the Hong Kong scientists play quite an important role in this. So we, I'm trying whenever possible, say with the authorities, like with the Health Bureau or with the Hospital Authority, we're actually trying to convey that. Actually in the audience, for example, we have Dr. Wong Kit-Fai, who is a prominent pathologist in Hong Kong, and KF and I actually have been trying very hard to actually persuade the Hospital Authority to actually have a special interest in next generation sequencing, because I think that ultimately that is going to impact on each of our health. You can imagine that you need to upgrade the health informatics system that, say, in 10 years' time when you go to see a doctor, they should consider your genome, and they consider your family's genome to advise you. And we need special law to protect us against, say, discrimination from various things, like, insurance, etc. And then, of course, like here, about people misusing this sort of technology, we also need guidelines. And we need the government, the legislator, we need the various colleges, in college and pathologists, in medicine, etc. But Hong Kong, unfortunately, has been quite slow in actually adopting medical genetics, because in the whole of Hong Kong, there's actually only 2 clinical geneticists, when we can probably do with 7 at least.
Okay, yeah.
Dennis, I got a question about the sensitivity and the accuracy for these tumor tests. And also, as you move on to test different cancers, are they going to be uniform as far as the sensitivity and accuracy on these tests? Thank you.
So far, the data suggests that this sensitivity is likely to be very similar for most of the tumor types, except currently the 2 which are the worst is a brain tumor and pancreas cancer. The brain I can sort of understand because there's a blood-brain barrier. But pancreas cancer, I'm not so sure. But maybe it's because there's a lot of enzymes in the pancreas which will digest the DNA as it leak out. But for the other, we're actually quite cautiously optimistic that we can be quite sensitive. Now, for example, there's some data I didn't have time to show you, is that you might have read in media that we actually are launching a nasopharyngeal cancer screening program based on this technology. And we actually want to study 20,000 cases. And so far, we're halfway there. We're 10,000. And with 10,000 healthy subjects in Hong Kong, we get 17 cases of cancer. And 16 out of 17 are early cancer. So we're cautiously optimistic this will work and will save life.
Okay. Professor He?
2 questions. The first question, how is the baby's DNA getting into the mother's blood?
Well, we think that because it's so nucleosomal in the size distribution, it's likely through some sort of cell death process like apoptosis.
Okay. The second question, I have never seen a medical doctor not so good mathematics. So I wonder if, I guess this is a time we have to get the information from DNA, and I guess there's a time for the mathematician and also computer scientists to work with medical doctors. Do you have any advice? How can the collaboration carry out?
Yes, I think actually we would not be able to do our work if we don't have very good collaboration from the bioinformatician. As a doctor, I only able to have a general feel about how you do that sort of analysis. But the actual way you do it, I need the computer scientist and the mathematician. And currently in my team, we have 10 bioinformaticians, and a minority of them are trained as biologists. But maybe a third of them are trained as computer scientists, and a third of them are mathematicians or physicists. So I think now is the time for this cross-fertilization of fields. And we definitely need your collaboration if you have time and interest in this area.
Okay. Yes.
Professor Law, thanks for the good words for bioinformaticians. I'm a bioinformatician, basically. So I was just curious that during your talk about Down syndrome test, have you ever encountered cases where the woman has multiple babies there? And
Yes.
if in that case, how would you be able to precisely detect whether each baby has the risk?
Okay, that's a very, very good question. Now, so if you look at this field, most people initially don't dare to touch on twin pregnancy. But then a couple of years ago, I decided to put this to a student of mine. This is his project. And then he actually developed a very interesting test. Now, as you know, in twins, there are 2 types of twins. One is monozygotic twins, so identical twins. The 2 twins are genetically the same. Another one is dizygotic twin, okay? So they are like normal siblings. So we thought actually if it's monozygotic, then you can actually look at that as being just one big baby, right? So the mathematics is no different from this. And then on the other hand, if it's dizygotic, then it will be interesting. Because you imagine, when I told you just now that the baby inherited flower from a father, right? If they are dizygotic, they will have different flowers. Sometimes they will have the same flower in one genomic region, and in some other genomic region, one twin will have one flower, let's say red flower, and the other one will have the pink flower. And so what we do is that when you measure the concentration of those different flowers in different parts of the genomes, the area where they inherit the same thing, the concentration is the highest. In those in which the 2 are different, then there will be different peaks. You can see 3 peaks. And then from the size of the peaks, I can work out how much DNA each twin is giving to the blood. And then you can also use that to deduce what is the chromosome 21 dosage. And I can even use that to monitor the health of the baby. And for example, recently we've been looking at some cases in which one baby unfortunately died. Then what happened to that signal?
Okay, first.
Yeah. It seems to me that your method is mainly best used for aneuploidy, for example, yeah, amplification, deletion, or number of chromosome count, they are different. What about changes that are, let's say, single point mutation, for example, in genetic diseases? Or, for example, there's a spice variant. I mean, would your method work, or should you use newer technology like from PacBio, for example, those smart, real-time sequencing?
That's a very good question. Actually, single nucleotide variation, we have also got a literature work there. We were actually the first group to talk about detecting those. We have actually detected the actual mutation which causes thalassemia. We published that in the Lancet in 2002. And we also use the technology to detect HLA types, so the immunology matching type. So the answer is you can do it. And for example, for cancer, that is some targeted therapy. Like for lung cancer, there's a group of drugs called tyrosine kinase inhibitor, ERISA. And we can actually tell that from the blood. We can predict if this lung cancer will respond to this drug or not. So the answer is yes, you can do this. But PacBio, unfortunately, is not a very good platform for that. And the reason is because PacBio, you have a machine which is 7 million Hong Kong dollars, but it can only analyze 150,000 molecules. And as you know from this talk, the more molecules you play with, the more accurate it is. So that is not a very efficient platform. So for those, digital PCR is a way to do it.
Thanks, Professor, for a very insightful talk in a very fascinating area. What I'd like to know is regarding the affordability of the test. I mean, basically, I think the more affordable this is, it's going to have a lot of impact.
Yes.
But what will be the kind of breakthrough that will be necessary to make it more affordable for the general public? For instance, do you think the computing power or faster computers, because we're talking about computation-intensive type activities, do you think those areas of advancement will actually help making things cheaper for the general public? Thank you.
Thank you for a very good question. Now, if we look at the cost of this technology, approximately half of it is on sequencing, and the other half is on the other things like DNA extraction, etc. And the sequencing side, actually the cost is going down very quickly. Now, for example, in computing, we have this Moore's law. So every 18 months, the computing costs half. But in actually sequencing, it has been dropping faster than Moore's law, so maybe 3 times a year, until more recently. And hopefully, within the next 2 or 3 years, when there are some other new sequencing platform that will arrive at in the market, that will further drive down costs. So I'm cautious and optimistic that it should be quite affordable soon. Now, for example, when we first launched the test in 2011, it was talking about $1,000 per test. But now some vendors is offering that for $2,000. And you're talking about 4 years.